Hi everyone. This is an example of a gas stoichiometry problem. We're going to follow our same four established steps with extra emphasis on interpreting the question to make sure that we can navigate our way through these choices in the correct way. Here we go. What mass of aluminum must react to produce 90.0 liters of hydrogen gas at 27.0 degrees Celsius and 125 kilopascals according to the following reaction, where we have some aluminum reacting with some sodium hydroxide and water to produce the rest. This highlights another thing that might happen. This is not a reaction that we ourselves could have predicted. So, good fortune for us, the balanced chemical reaction was provided right in the question. That is so nice, and it saves a bunch of time, and it saves us a bunch of work. Balance the equation, already done. How nice is that? Which means we can move on to the interpretation. Let's look at what we have. What mass of aluminum must react? That's what we're looking for. We're looking for the mass, so I'm putting an M with a question mark here under the aluminum. Already I'm thinking about, I'm looking for mass in the end. What's going to happen down here in the end? That's where the question mark is. That's R. We have some givens. Look at that, 90.0 liters of hydrogen gas. The hydrogen is way over there at the end. We have 90 liters. The volume, 90 liters. What flashes through my mind is, yes, the volume's already in liters. I don't have to do a unit conversion. That's so good. Hydrogen gas at 27 degrees Celsius and 125 kilopascals. This and links those two numbers together, and the at both links them with the hydrogen gas. So the temperature here is 27.0 degrees Celsius. I'm already thinking, I'm going to have to convert that into Kelvin. And 125 kilopascals, that's the pressure. Well, where the question mark is the R, all these other numbers, G. We have interpreted the question. The equation was balanced and given to us. That was so nice. What volume of aluminum? That's required. The rest of the labels over there under the hydrogen. We can move on to step 2. Let's find moles. Find moles. Questions still sometimes might straight up tell us the moles. We will sometimes find moles by reading. Do we have a mass to do mass over molar mass? We do not. C times V? No. The question does not mention STP or SATP. We're not using Avogadro's law. That leaves us the ideal gas law. P times V over RT. We have a P, we have a V, R, the ideal gas constant. We already know that. We have the temperature. So we're starting with P times V over RT, which is the pressure, 125 kilopascals, times V, 90.0 liters, over R, that's 8.314 kilopascal liters per mole Kelvin, 8.314, times the temperature in Kelvin. That's our 27.0 plus 273.15. 273.15 Kelvin. If we want to do the temperature conversion separately first, put the raw answer in there, that does the trick. If at this point we need to hit equals on our calculator to be extra methodical, that's okay. I would encourage you just to keep this step here and move on to the next step. Multiply by R over G. We have these nice labels. Here's the R balanced with a 2. Here's the G balanced with a 3. R over G times 2 over 3. All of that work, whatever we're doing for the first part of our calculation and the mole ratio is red N. That's red N. We're looking for the mass. Here, in step 4, there's only one formula that gives us to the mass. It's the red N multiplied by the molar mass. So here, we're going to multiply by the molar mass. We're looking for the mass of the aluminum, so we're going to use the molar mass of that same chemical, which the periodic table tells me is 26.98 grams per mole. We have the whole calculation set up. Let's get to pushing buttons. 125 times 90 divided by 8.314 times 27 plus 273.15 times 2 over 3 times 26.98. Calculate this out with me. See if you can follow and get the correct answer. If we have this set up correctly, it would be a shame if we didn't arrive at the answer because our calculator let us down. We end up with 81.08767,363, which, when I go back to the question, 90.0, 27.0, and 125 have 3 significant digits, so I need to round this off appropriately. 81.1. This was the mass in grams. When we have a gas stoichiometry problem, there's lots of things that could happen. We might have to work out the equation ourselves, balance it ourselves. There are going to be times in solution stoichiometry as well, or gravimetric, where just the equation is provided to us. That can save us a lot of time and energy. We're always going to be required to do some interpretation and to make some choices about how to navigate through these steps. If we have everything set up correctly, let's also make sure that we arrive at the answer. It's always a shame to have all of the numbers in all of the right places, but have our calculators let us down. And as always, watch those significant digits and units. I hope that helps.